Welcome to my talk. So my name is Thomas, and my presentation today is going to be on the investigation of unsteady aerodynamics with application to airborne wind energy, with a focus on turbulence, turbulence-induced unsteadiness. So to get started with my talk, I want to look a bit at our motivation. Why do we want to look at unsteady aerodynamics? So especially in the context of airborne wind, we want to be able to properly assess what the forces that are acting on a kite, how they are. Because we want to be able to steer our kite. We want to make sure that we cannot succeed some design limits, or also we want to make sure that we can assess the right performance of our system. So to illustrate this motivation, I took this picture from Kitecraft, which shows the most recent prototype on the test site in southern Germany. And we were thinking of what are the different aspects that can influence unsteady aerodynamics. So we have, of course, the aerodynamics that are due to the design specifics of the system. So in the kite, for the kite of Kitecraft, they use a box plane structure. They have stuff, shows of airfoil, shows of taper, and this will, of course, then define a lot of the aerodynamics of the system. The second aspect are the dynamics of the maneuvers that they fly. In the present case, you can see the kite is in hover motion, and then eventually will transition into a power production phase, or maybe into launch phase. So here also you will change from one certain operation phase into another. Have a lot of unsteadiness that will change the aerodynamics of your aircraft. And the third part that we can also look at are environmental conditions. So in this case also, what we can see, we have the aircraft that is operating on this flat terrain that is surrounded by a forested area. So depending on the direction of the wind speed, the wind conditions in which the system will operate might change quite drastically. So how do we actually investigate unsteady aerodynamics? We have maybe two approaches, or two high-fidelity approach, let's say. We can look first at the ring-resolved aerodynamics. So when we focus on the very local flow patterns around the wing, in our case, for instance, here we can look at the pressure distribution on the wing. We can look at the induced tip vortices, how they affect the near wake of the aircraft. So that would be one approach that focuses really on the specifics of the system. For this, I may also want to refer you to the work of my colleague, Niels. And a second approach would be to look more at turbulence-resolving aerodynamics. So in this case, we're more interested in the large-scale structures of the wind that we can, for instance, capture with large-eddy simulation. The problem here, one aspect of this kind of simulation, is that we cannot capture what is really happening directly at the wing, because we model the system as an actuator line that relies on static polar processes. So this brings me to my research objective. So we want to actually be able to try to capture a larger range of scales of the flow patterns around our aircraft. So we want to be able to capture the combined wing and turbulence-resolved aerodynamics of the aircraft. So this is, for us, fairly new research, so we try to build up our framework in an iterative method. So the first step, we have geometry-resolved simulations, where we focus on the very local aerodynamics of the kite. We then move on to turbulence-resolved simulations, and we want to actually then combine these two types of simulations using hybrid LES and TMA. So in the remainder of my talk, I want to walk you through these three different aspects of our framework. So moving on to the geometry-resolved simulations, we start by using the MegaWest reference aircraft. So this is an academic reference system, of a large-scale system that is meant to generate several megawatts of power. It's a very large aircraft with a wingspan of 42 meters. And then to look at the local aerodynamics, what we usually do, we build a body-fitted 3D mesh around the aircraft. Here we opt for a C-shape that allows us to change the inflow conditions, and then we use unsteady runs to to look at the flow field around the aircraft. So this allows us to very much capture the forces that are acting on the aircraft based on the flow characteristics. This would be our first part. The second part would be the resolved turbulence simulations. What is typically done in LES, we can use large precursor simulations that are able to capture lots of the different structures in the atmospheric boundary layer. Here in our work, we will choose a different approach where we generate turbulence using Mann's model. So we have synthetic inflow turbulence. So what we actually have, we have a 3D region that is at a frozen field of turbulence. And what we do, we take some slices of that flow field that we introduce as time-varying inflow condition to our larger domain. So at the time instant t0, we can take one certain slice, and at the next time step, we can take another slice, and we can then advance our simulation. And so we solve this usually with the LES capabilities that are available in OpenFlow. So in order to couple these two aspects, we use hybrid runs LES Chimera. So I will first focus on the Chimera approach. So the Chimera approach is an overset mesh coupling technique where we actually take two separate meshes. So we have, for instance, in green our wing, and around this wing we then build our overset mesh or our component mesh that we want to refine, to resolve quite refine in order to capture this local aerodynamics. So this is really, we focus mostly on this region of interest around the kite. Around this box we can then build our background mesh. Here in this picture is shown relatively small, but this is the region that we want, that we can easily increase in size to capture maybe larger parts of our flight path. So how this method works, to show this in a simplified manner, so we have calculated cells of our domain. These would be the blue ones. We have interpolated cells. This is where we interpolate the solution from one mesh to another. And we have then in red whole cells. So in this case here, what we have, we take our background mesh that will provide some kind of boundary condition to our body mesh. And in the next step, we can then take from the calculated cell inside our overset mesh the forces on the wing or the flow conditions around the wing and interpolate them back onto the background mesh to then have the influence of the flow of the wing, on this background flow field. Next, we can look at how we want to handle turbulence. So we opted for a hybrid runs LES simulation technique. The idea of this technique is that you can use LES in the separated region of your flows, where you have maybe large separation on your wing or turbulence field of the wind field, and a runs condition close to your wing, where you have more separated, where you have attached conditions. And so here it's, maybe the color scheme is not the best chosen for the slide, but you can see in red the region that is solved with LES, and in blue the region that is solved with runs. So as I mentioned, runs behavior is more likely seen in the direction around the wing, LES more in the external flow. But in our case here we also have, I need to mention this, somewhat unexpected runs area in the wake, but this is due because the grid that we have in this example is just not fine enough to be able to capture this scale. And so in building up this framework, we've worked on a little proof of concept where we want to look just at steady level flight. So we consider there two examples. The first simulation will just be our unsteady run simulation, where we use a K omega SST model. The inflow condition to our domain is about 80 meters per second. This represents like the relative wind speed that the aircraft would see, with a turbulence of about 1% turbulence intensity. And the second simulation that we have then is this hybrid runs LES simulation with this resolved turbulence. So I can give you some results of what we've been able to capture with this approach so far. So the plot on the left shows you the pressure distribution on the suction side of the wing, so on the upper side of the wing, the pressure distribution that is then normalized with the reference pressure distribution from the RONS simulation. So what we can see in blue, we show the pressure distribution for the RONS simulation, and in green for the hybrid RONS-LES simulation. And what we're happy to see is that we actually, with this hybrid RONS-LES simulation, we're able to capture the fluctuations of the forces. So this green shaded area that you see, this is the range of, let's say, pressure forces that we have on that wing. So we can clearly see that this has quite an impact on the loading that the wing can, for instance, see. And then we look how this integrates into more known performance metrics such as CL and CD. And we can clearly also see the effect here. We have the green line, which is the hybrid simulation, and blue, the reference simulation, where we have this pattern of, let's say, kind of sine wave. And this pattern is actually seen here because the man box that we use enters 3 times the domain in this specific case. So actually this fluctuation that you see is the reoccurring passage, let's say, of a certain flow feature from the turbulent wind field. All right, so as this is a first step for our framework, we are currently also working on improving this framework. So the first step in our improvement is to increase the quality of our mesh and also its resolution, because this was very coarse results, just to show that it's working and that we can capture these unsteady effects. But what we also want, we want to be able to eventually capture more transient phenomena directly at the wing. So here you can see like a separation region behind the, closer to the back of the airfoil. And then also we want to include mesh motion capability. So that's also one big advantage why we use overset technique, is that we can actually have a background mesh that we build once that is fixed, but then we can actually move our component mesh quite easily into this domain. And this brings us then to the future improvement that we want to do, because we want to add some aero-servo-elastic capability to our framework. So the first step would be to add the inclusion of a full trajectory. So what we want to do, we want to couple our framework with the toolbox box, which generates the full trajectory that the kite would fly. So what you can see on this trajectory, for instance, is the kite that is flying 4 loops in power generation in blue, and then you see the green part is the retraction phase of the kite, so this typical pumping mode behavior that the kite might fly. And eventually, I invite you to go to the talk of my colleague Niels Penna tomorrow, that will already show some preliminary results using this kind of trajectory in our geometry resolved simulations. And eventually we'd like to also try to couple our CFD framework with a low order deformation model for the wing to be able to see how the effects of these maneuvers, for instance, changes the loading of the wing. So maybe we've seen in the previous talk, for those of you who might have paid attention, you really see actually how the wing can bend. So this is really some effects that we want to be able to capture with this kind of framework. So as conclusions to finish my talk, so we've been looking at this geometry and turbulence resolved aerodynamics. We've explored the use of overset approach and hybrid RONS-LES technique for this application. And we're working now with our proof of concept towards integrating this into a full aero-elastic, aero-servo-elastic framework. So I'm happy to take any questions from you that's there on my talk.
So could you please go back to slide number 9, I guess? Yes. So what I'm interested in, that actually in this overset technique, was there any boundary layer around the wing, around the wing mesh?
You mean directly at the wing?
Yeah. I mean, I guess it was, just I was also working with the overset mesh technique
Okay.
in OpenFlow,
Yeah.
and I was facing with many difficulties, especially it was super slow. So that's why I know that it works quite well without boundary layer, but I was just curious, did you use boundary layer here?
So in here, our mesh is really very coarse. We cannot really capture much of the very local aerodynamics, and in that case, so this is something we're currently working on to really improve the mesh. Or you mean boundary layer from the background?
No,
So really at the wing, yeah?
At the wing, the foreground, but on that picture it seems that it had, right? On the top right. I mean, there was a...
The result which I mean, of course, we refine our grid towards the upper.
Yeah.
To be able to eventually capture these effects. Right now we don't capture them properly because the mesh is way too coarse.
Yeah, alright, okay. Maybe I had problems with the motions because, so good luck with it. Our outcome was that we both CFD solvers.
Okay. But I would be happy to discuss this, your experience more in detail afterwards, because as I mentioned, this is quite new work also for us. My background was more in actuator line and NES simulations, so this is also fairly new. So I would be very happy that we discuss this later.
Yeah, I'm happy to speak.
Another question, maybe?
Actually, yeah, since kind of along those lines, I wondered if you did like a mesh sensitivity study, but probably not yet.
Not yet.
But I guess then further comment there, you're using k-omega SST for those variants, yeah?
Yeah.
Then I guess in this limit, the effective Reynolds numbers are small enough, or are you using in that model, if you have any low Reynolds number corrections, or what's going on there?
We had quite high Reynolds number, we haven't looked into this.
The effective Reynolds number, so when you under resolve, right, the effective Reynolds number is down, just like anything else.
Okay.
It's hard to do.
Yeah.
I was just curious about that.
We haven't looked into this.
You showed that spread on the bottom. You showed this kind of spreading Rance regime. Is it giving any goofy case?
So we haven't really looked in that much details at the moment for this. We're looking at what different models are available also in OpenFlow, and we see that we have quite different behaviors from one model to another. So this is really something we still want to investigate, because some are able to, in some cases the wave is really full LES, some part of the waves are really long, but it really, from the tests I've made, this performance really decreases when you have a close mesh. So actually it's really depending on the mesh. So there's really some work that we really need to dive into to make sure that we have the right choices for the pilots.
My question is actually, I'm not a CFD expert, so forgive me for my ignorance, but when you project the turbulent fluctuations onto the Rans mesh, and then eventually it gets affected to the wing, by going to sort of an unsteady Rans, does it still sort of preserve these large-scale fluctuations once it hits the wing, or is it?
So in the full unsteady Rans case, that would be this one, for instance. We haven't put the turbulence in the inflow because we would expect also that it's just like it's then fine. So for the second case, there we have turbulent inflow, which is then also resolved with the LES more like method.
Yeah.
But also there also some the intensity of your fluctuations get lost as you progress in the so there's also some aspect that need to be definitely taken care of.
Thank you.
Would you have just a comment on if you have any faults on the stabilizer, if you want to include that also the tail, or like when you go to the aerocycloelastic simulation.
So as you see right now, we don't even have a tail. So that's also some work in progress. That well, in that moment, and for now we really don't have any motion, so that's actually what we don't need to do with the tail. But it's indeed the idea that we want to couple this with Alibox, where we would then get, for instance, the control inputs from optimal controller that will tell us eventually how you have to steer them or handling it.
Thank you, Thomas.
Quite a few questions from the front here. Yeah, I think we need to move on. Thanks again.